Hey, welcome. I have prepared a little assessment here to test your knowledge of acid-base chemistry. So try these problems, and I will then post a solution key to these as well, um, today or tomorrow. So the next several slides contain these problems. Each of the following Bronsted-Lowry acid-base reactant pairs results in a favorable acid-base reaction. This is what you're told. You are to complete the products, the structures of the products, and then rationalize why the reaction proceeds in the product direction, right? In other words, explain why that reaction is favorable as written to the right. And so there are 6 of these problems, A, B, C, D, and E, on this slide and the next 2. Here are the 3rd and 4th problems of that type. Here are the 5th and 6th problems of that type. So you will learn when you take organic chemistry and when you study the chemistry of alkynes, right, carbon-carbon triple bonds, that a good way to prepare alkynes is by a so-called double elimination of HX, where X is chlorine or bromine, as you can see in the first transformation at the top here, right? We take that dichloride, we react it with 2 equivalents of potassium tertiary butoxide, right, which is the conjugate base of T-butyl alcohol, which is a fairly strong base, and we get a good yield of, in this case, the internal alkyne from removal of 2 equivalents of HCl. However, when you try the same method and the same chemistry to prepare the terminal alkyne, that's the middle transformation, you do get some of that product, but you also get the vinyl halide, right, as a byproduct. You can see that as the second product, and you get a very low overall yield. Finally, when you use 3 equivalents, and I'm sorry, that middle transformation, that 30% yield, that is using 2 equivalents. Again, 2 equivalents of potassium T-butoxide. I'm sorry, that should be more clear. However, when you increase the stoichiometry and use 3 equivalents of base, 3 equivalents of potassium T-butoxide, followed by dilute aqueous acid workup, you get you're back to, again, a very efficient, very good yield of the desired product, which is the terminal alkyne. You are to provide an explanation for the difference in behavior, right, using essentially the same chemistry, except for the stoichiometry, between the preparation of internal versus terminal alkynes. Okay, finally, you're told this particular bicyclic ketone, this is a bicyclic molecule. You've seen quite a few examples of ring compounds, cyclic compounds, or you've seen polycyclic compounds where rings are fused together, a 6 with a 6 or a 6 with a 5, whatever it might be. Excuse me. This is an example of a bicyclic system which has a bridge. Okay, instead of a fused ring system, it's a bridged ring system. It's a bicyclic system. This particular ketone has a pKa of 34, which is very high, very, very high for ketones with removable alpha hydrogens or enolizable hydrogens. You are to provide an explanation for why the pKa of this molecule is so high, or why the acidity is so low. Okay, and the hint is to make a model. So give these problems a try. Now, what I haven't included here, but you are free to use and you are encouraged to use, you're encouraged to use a pKa table, like the one that you saw in one of the lectures in the mini course, or perhaps your own pKa table. But you're certainly free to use a pKa table that will give you functional groups and their approximate pKa ranges. Okay, you're encouraged to do that. All right, good luck with these problems, and I will work on the solution key.